All right, let's jump right into this explainer on Caldwell 73. This is a star cluster that's hiding some of the absolute most bizarre extreme objects in the known universe. If you are fascinated by the absolute limits of physics, you are definitely in the right place today. We're going to unpack a recently uncovered cosmic mystery that's literally forcing astrophysicists to rethink how massive certain stellar remnants can actually get.
Think about this number for a second, 3.887. Now, what's wild about this is that it represents the total mass, in solar masses, of a very specific, totally mysterious binary star system. That means this system weighs almost 4 times as much as our own sun. But honestly, it's not the total mass that's shocking. It's how that mass is distributed between a rapidly spinning pulsar and a companion object that, frankly, defies our current understanding of physics. To get why this is so weird, we need to zoom out and look at where this system actually lives.
Section 1. Inside Caldwell 73, the crowded stellar city.
So let's start wide. Caldwell 73, or NGC 1851 if you prefer, is a compact globular cluster. Basically, it's an ancient spherical city of stars, bound super tightly together by gravity, sitting way down below the galactic plane. Because its core is just absurdly dense with stars, it acts as a massive, highly fecund seedbed for pulsars. It is this chaotic, crowded environment where stars are constantly bumping elbows and interacting with one another. The recent TRAPUM survey actually gave us a phenomenal look into this cluster. Using the MeerKAT radio telescope down in South Africa, researchers found 13 new pulsars, bringing the cluster's total known up to 14. That ties it for the third most pulsars in any known cluster. What's crazy here is that these pulsars aren't just scattered randomly. They're all jammed right inside or just barely outside that ultra-dense core. It's an even split. Half are flying solo and half are locked in binary systems. And almost all of them are millisecond pulsars, which are dead stars just whipping around hundreds of times every single second. Section 2. The Cosmic Dance. Chaos in the Core. Right, so the crucial piece of the puzzle is understanding how this jam-packed environment forces these stars to interact. It sets up something called a secondary exchange encounter. Think of the core of Caldwell 73 like this utterly chaotic cosmic dance floor. First, you've got a dead pulsar that gets spun back up to insane speeds by feeding off a lighter companion star. They're happily dancing. But then, because it's so crowded, a massive, dense intruder wanders too close. Gravity takes the wheel, a completely chaotic interaction kicks off, and that original lighter partner gets violently kicked off the dance floor entirely. Finally, the pulsar and this heavy new intruder get locked into a brand new, highly eccentric binary system. It is literally stellar theft on a cosmic scale. And because of those chaotic ejections, the binaries we find in Caldwell 73 are totally unique. Out in our regular galactic disk, binaries have this super predictable evolution, right? They settle into nice, calm, nearly circular orbits. But in a globular cluster, these things have wildly eccentric, stretched out oval orbits. They actually carry the gravitational scars of those chaotic stellar collisions and exchange encounters we just talked about. Moving on to Section 3, meet the eccentric pulsars, the extreme trio. Okay, let's meet the 3 specific pulsar systems making Caldwell 73 so famous in the astrophysics world right now. Pulsars A, D, and E. The data on these secondary exchange products reveals just how extreme they really are. Consider their orbit eccentricity, where 0 is a perfect circle. We're looking at 0.89, 0.86, and 0.71. Orbits that stretched out are incredibly rare. And look at their companions. Pulsar D snatched up a massive carbon-oxygen white dwarf. Pulsar A likely grabbed another neutron star. But Pulsar E, with a massive companion weighing somewhere between 2.09 and 2.71 solar masses, that is the real mystery here. Actually, scratch that. Before we dive into Pulsar A, I have to point out just how intense the gravity is in these eccentric systems. For Pulsar A, astronomers measured an Einstein delay of 0.0216 seconds. That might sound tiny, but it's the largest relativistic delay ever recorded for any binary pulsar. Because that orbit is so eccentric, as the pulsar whips close to its massive companion, the sheer speed and intense gravity literally warp time. From our perspective on Earth, it looks like the pulsar's ticking slows down. It's Einstein's theory of general relativity playing out in real time. Section 4. The Mass Gap Mystery. The anomaly of PSR J0514-4002A-N. So let's get back to Pulsar E and the sheer anomaly of its companion. You've probably heard of the mass gap. It's this highly debated region in astrophysics. Basically, it's the elusive boundary between the heaviest known neutron stars, which max out around 2.2 solar masses, and the lightest known black holes, which usually start around 5 solar masses. Theoretically, compact objects in this gap just shouldn't really exist, or at the very least, they are exceptionally rare and we don't understand them very well at all. Well, by meticulously tracking the radio timing residuals across years of data from MeerKAT and the Green Bank telescope, researchers were able to precisely weigh the system. The math pinpointed the companion's mass squarely between 2.09 and 2.71 solar masses, meaning it sits right smack in the middle of that mass gap.
Section 5. What is the companion? The optical hunt.
To figure out what this thing actually is, astronomers had to first rule out if it was just a really heavy, normal star. If this companion was a regular hydrogen-burning main sequence star, a blue straggler, or a red giant, our optical telescopes would easily spot it. I mean, an object well over 2 solar masses that is actively burning fuel would be super great against the backdrop of the cluster. But when astronomers pointed the Hubble Space Telescope directly at those exact radio coordinates, they found absolutely nothing. The space is entirely empty in the optical spectrum. There are stars nearby for sure, but not a single one at the exact mathematical location of our binary system, which proves, beyond a shadow of a doubt, that this companion object is completely dark. And that brings us to this incredible conclusion from the research paper. Quote, "The companion is a compact object, and its mass is in the mass gap, so it either is a very massive neutron star or a low-mass black hole. Since it doesn't emit optical light, it absolutely has to be a dead, collapsed remnant. But it's heavier than any neutron star we've ever confirmed and lighter than any black hole we've ever found."
So how on earth does something like that even form? The leading idea right now is the merger theory. Basically, what you should take away from this is that this companion is likely a cosmic Frankenstein. It's way too massive to have formed from just a single star collapsing. Instead, it's highly likely that a long time ago, 2 separate neutron stars collided and merged into this one massive object. Then, years later, this heavy merged remnant went wandering through the crowded core of Caldwell 73, crashed that cosmic dance, and snatched up Pulsar E in a secondary exchange encounter.
Caldwell 73 really isn't just a cluster of stars. It's acting as a natural laboratory, pushing the very limits of gravity, relativity, and stellar evolution. Finding an object sitting perfectly in the mass gap completely changes how we view the life cycle of the universe's most extreme matter. And it leaves us with one incredibly provocative question. If a cosmic Frankenstein like this was hiding right under our noses, just how many more impossible, physics-defying systems are still lurking in the dark core of Caldwell 73, waiting for MeerKAT to find them? Keep looking up, you guys, because the universe is always weirder than we think.